Okay, so we welcome Ludovic van Waerbeke, and he's professor at the University of UBC in Vancouver. He's done a lot of work on weak lensing, so C-T lens, for example, and more recently in unions. But today he's not going to talk at all about weak lensing, but rather on a new way to describe dark matter. So thanks, yes.
So this is a colloquium level talk. And my goal is to present a new model for dark matter, which people have not heard about, but in my opinion, I'll try to convince you has lots of interesting aspects of it. And one of them is that it can be tested, that it leads to predictions that can be tested today with current technology and even more with forthcoming technology. But the talk is really in two parts. So the first part is more like a general discussion motivating the model itself. And I will switch to the second part where I present the model, and I will give you the tools you need to actually make calculations and make predictions if you want to use the model. So let me start first part, a general discussion, justification. Why do we need to go away from the standard paradigm of WIMPs? Through my talk, I'm completely ignoring the possibility that gravity could be modified. So with that in mind, basically, there is no doubt dark matter exists. Just ignore the fact that gravity could be different. So when I was, yes.
The slides are not.
Oh, they're not moving on the screen? Aha. Okay. Stop sharing, share again. Yeah. Because I think I'm full scale. I cannot see my presentation anymore. Share here, yeah. I don't know what's going on. So let's see. What about now?
Try to change this. Yes, now.
It works? Okay. So when I was preparing the talk, I was curious to see what a place like the CERN has to say about dark matter. So I went to the CERN and look for dark matter page, and this is what they say. So they say, unlike normal matter, dark matter does not interact with the electromagnetic force. It means does not absorb, reflect, or emit any light. In other words, I basically rephrased what it says on the page, and I rename it like the dark matter paradigm. Basically says dark matter is dark, it's non-interacting, and it's made of non-bionic stuff. And this is really the thing you read in every textbook, right? So that's what I call dark matter paradigm. The point is, trying to make the first part of this talk, is that there is actually no observational evidence for any of those points. I try to convince you that every single point here you can actually forget about. So that being said, there are theoretical motivation for why the dark matter paradigm exists. And you have to go back to the 80s, 90s, where people realized that in the context of supersymmetry, you can predict that there are new particles, so weakly interactive massive particles, that turns out to have the right mass. They are generated as thermal relics in the electroweak phase transition. Turns out that they have the right mass with no tuning, a couple of hundred times the mass of the proton, which naturally leads to the right order of magnitude for omega matter today. No fine-tuning whatsoever. So this is why people were impressed. They call this the WIMPs miracle. And the general thought was, okay, if it works so well, so it must be true. And from that, essentially, the WIMPs miracle became like justification for the dark matter paradigm. So that was in the 80s and 90s. But by some sort of logical inversion, the dark matter paradigm became a paradigm, the basis for justifying, what dark matter should look like. So there was some kind of logical inversion where dark matter paradigm was taken as the truth, from which that becomes a support for WIMPs or WIMPs-related dark matter. But the reality is the dark matter paradigm is a consequence of the WIMPs miracle, not the opposite. So let me go through the deconstruction of the dark matter paradigm. Let's start with the point number one. You can see it. I don't think I can hide this thing here. Yeah. Thanks, great. So, so remember in the dark matter paradigm list I had, the first one was dark matter is dark. In itself, that sentence doesn't mean anything because nothing is dark in an absolute sense. So it's always dark relative to something you can or cannot detect. If you look at the brightness of the sky as a function of wavelength, start radio, go up to gamma ray. And so these are actually measurements. I did this very stupid calculation where I assume dark matter is made of objects the size of Jupiter, which are black bodies. Right? So imagine dark matter is just Jupiter-sized things, black bodies everywhere. The emissivity of the sky you will get, so would be roughly here, black bodies at temperature of 20 so you're roughly looking at this frequency range here. They would barely make it up in the plot here. So if you assume a very stupid model, dark matter is made of Jupiter-sized things, which are black bodies, you would not detect it. So it's not actually true to say dark matter is dark. It's in a certain context.
Can I?
Yeah.
I mean, isn't that just saying it's not electromagnetic?
Exactly. The whole discussion is about electromagnetic. Yes. Point number two, when we say dark matter is non-interactive, what do we actually really mean here? So talking about interaction rate, so how many times you have a collision per second, goes like this. So gamma interaction rate can be written as the number density of the species you are looking at, times cross-section, times delta V, which is the relative velocity between the two particles that are interacting. So look at that, say, okay, very small cross-section, which is the case for the WIMPs, allows for very high number density. So if cross-section is very small, you actually need, for a given interaction rate, a large number of particles. But the thing is, you should not forget that what you can constrain observationally is not an X, it's the mass density. Number density is not accessible to observations. Mass density is accessible to observations. So if you think about what that means in terms of observations, look at the Earth-Sun system. Typically, inside the Earth orbit, the sphere defined by the Earth orbit, you have approximately a few times 10 to the 16 gram of dark matter inside it. In the WIMPs paradigm, where dark matter particles have typically the mass of 100 times the mass of a proton, can calculate number density is approximately 1 per cubic meter. So indeed, in that case, we have dark matter particles everywhere. We are constantly bombarded by those particles in this very row. What if, instead of having a very low mass for particles, you have only one particle with the same mass? And let's say it's nuclear density. So it's actually very small, despite its large mass. The number density suddenly becomes really small, but you haven't changed anything regarding the interaction rate. So you can rewrite the interaction rate gamma from n sigma delta V as sigma over m times mass density times delta V. I haven't done anything here but inserting the mass of the dark matter particle. So what you learn from this rewriting of gamma is that dark matter is physically not characterized by its cross-section. It's physically characterized by what I call the reduced cross-section, which is sigma over m. The consequence for this is the dark matter could be many things. It could be very low mass with even very, very low cross-section, which is the WIMPs, but it can also be high mass and not so low cross-section. In both cases, you would pass observational constraints easily. So what do we know on the observational side? What do we know about sigma over m? There are actually quite strong constraints, but they are in fact not that strong if you think about it. If you look at the distribution of large-scale structure from, say, the mass power spectrum you get from lensing or other observations, you want so if the interaction is too strong, this will have the same effect as warm dark matter. We tend to dilute the structures, and it will tend to change the power you get at very small scale, basically to decrease it. We don't see that. Dark matter is cold. So that implies that sigma over m must be less than a certain number. This is what you get, the number you get from large-scale structure constraints. If you ask the same question now, you look at things like cluster of galaxies with hot gas inside. Imagine dark matter interact with the hot gas. Again, we don't see that. What does it mean in terms of sigma over m? This is the number you get with current constraint. So sigma over m, so interaction between dark matter and baryons, much over m, much be less than this number, 0.03 centimeter square per gram. The strongest constraints come from the CMB. We do not want dark matter to be in thermal equilibrium with the photon gas. That's clearly not what CMB shows us. So from the CMB, the tighter constraint you get, sigma over m, should be less than 10⁻⁷ centimeter square per gram. These numbers are small, but they are much bigger than what you get for the WIMPs. Typical sigma and m for WIMPs gives you a ratio of 10⁻20. Anything between 10⁻20 and 10⁻⁷ would be a viable dark matter candidate. It would totally behave as cold dark matter. So there is a lot of room here. Yes.
So what about from direct detections, you get loser bounds?
Direct detection is way worse, because if you think of that extreme case, if you build a direct, a detector on Earth, you basically will never detect your dark matter particle in that case.
So direct detection only works if the mass is
exactly. Exactly. It only works if your n is high enough. So the last thing, when we say dark matter is non-baryonic, what do we actually mean? We know the argument is BBN sets that constraint. Now imagine instead of having 5 times dark matter has ordinary matter, let's imagine you say, okay, all matter is ordinary matter. So you multiply omega b by 6. You know the consequence of this is a disaster, because you decrease the number the abundance of deuterium by factor 20. You change the abundance of helium-3 by a factor 2, and you also change significantly the lithium abundance. So that clearly does not work. But it does not work. Again, we have to be very precise and specify the context why it doesn't work. What BBN implies is the dark matter cannot be made of baryonic stuff if that stuff is made after BBN, because we don't want these baryons to interfere with the BBN chemistry. So that rules out right away stellar remnants as candidates for dark matter. That has been known for a long time. On the other hand, this argument, this BBN argument, does not rule out dark matter objects made before BBN. And a good candidate for that everybody knows about is primordial black holes, because they are made before BBN. So you basically hide your baryons before BBN, you are safe. You are not messing up with BBN in any ways. And there are other candidates, there are other models. I will quickly go through them in the next 2 slides. So PBH, it still have active field of research. I will not discuss that. If you are interested in a review, when I was preparing this talk, this review, I came across it. It's very up to date and very interesting, worth reading in my opinion, if you are interested in PBH. So in other words, the dark matter paradigm where dark matter is dark, non-interacting, made of non-baryonic stuff, none of this is necessarily true. And in fact, all of these statements could be not true at the same time. So those models which violate the dark matter paradigm are called macros, and it's known under the name of macros in cosmology. So just to finish the first part of my talk, to answer the title of my talk, which is why is it so difficult to probe the nature of dark matter, or maybe because we are not looking for the right thing at the right place. We are expecting WIMPs for historical reasons, but if they are not WIMPs, if they are macros, we completely miss them. We completely miss the point. So macros themselves, it's not new. It has been around for quite some time. The first, I think, mention of macros in a modern cosmology context came from PBH. But then quickly after that, different people developed different ideas. Ed Wheaton had his strange quark nuggets ideas and many others. The list is much, much longer than that. All these models are part of the standard model of particle physics. You don't need wild extensions. You actually don't need extensions at all of the standard model of particle physics to make this work. With a mild extension of the standard model of particle physics, you have a model like the one I will talk about today, which is the AQN model. And if you are looking at models with wild extensions of the standard model, this is actually what is most popular today. So in cosmology in particular, cosmologists they do a lot of work in the context of ULAs, ultralight actions. You also have the stereoids neutrino, SITM, and many other things, and variants of the WIMPs as well. So these are way beyond the standard model of particle physics. They are BSM candidates. And why BSM candidates? Why is it so popular? That's just me, but in my opinion, that's because we assume the dark matter paradigm is true. And if indeed the dark matter paradigm is true, we don't have any options. If dark matter paradigm is true, dark matter is dark, non-interacting, and non-baryonic, pretty much the only thing that fits the bill is BSM candidates. Well, we know WIMPs have some difficulties. We know non-discovery of WIMPs is currently a problem. So, people start thinking seriously about going beyond the WIMPs. So standard model of particle physics, in a way, cosmologists think that is still the most successful physical theory in existence. So just as a parsimony principle, Occam's razor principle, if it is still possible to explain dark matter within the standard model, we should just keep trying until we are sure this option is dead. At the moment, there is no evidence that it is dead. So the standard model has some problems, particle-related problems which have nothing to do with cosmology. I will just mention one because that's the one that is at the origin of the axion quark nugget model I'll talk about in the second part of my talk. This problem is a strong CP problem, which is the fact that the neutron doesn't have an electric dipole. And it was solved in the, I think, late 60s, by introducing a new particle called the axion particle with a specific coupling. So it couples in the hadronic mass range. It's called the QCD axion. So the QCD axion was specifically introduced to solve the strong CP problem. So this is where the axion quark nugget story effectively begins. So the idea was initiated by my colleague at UBC, Eric Zitnitsky, who is actually one of the co-inventors of the QCD axions. Talking about the formation of dark matter within that context is a talk in itself, but today I really want to focus only on the cosmological signature of this. So I will basically make a long story very short. What do we have? If QCD axion exists, my colleague showed that you basically form nuggets of matter and antimatter. Why matter and antimatter? Because the way the axion couples to matter triggers a formation phenomena which happens at the quark-hadron phase transition. So way before BBN energy scale is about MeV scale, and the quark-hadron phase transition is 170 MeV. So it's way before that. It's roughly the same time as protons and neutrons were formed. So this coupling between axion and matter, antimatter, again, at the same time matter and antimatter starts to annihilate, nuggets naturally form, nuggets of matter, nuggets of antimatter, which tends to grow until you run out of matter and antimatter to make them grow. So you have those nuggets that form in that early time, nuggets of matter, which are called quark. Technically, they are in color superconducting phase, but it's irrelevant for what I want to talk about. And you have nuggets of antimatter that grow as well. Again, this formation process is happening at the same time hadrons are being formed. And at the same time, matter-antimatter annihilates massively. So this nugget formation is still a very minor phenomena. Dominant phenomena at the time is still matter-antimatter annihilation. You have 10 to the 10 photons per hadron. So you have those nugget formation, you have a leftover of matter, which forms the hadron, us today. But most of the action is not this action. Most of what happened at the time is the matter-antimatter annihilation. So you have those nuggets. that form, and at the end of the phase transition, they are there. They constitute our dark matter today. So you have the matter nugget, which might become neutral, so they are surrounded. It's actually also a cross distribution of electrons, which ensures the quality of the system. For the antimatter nuggets, you have positrons. Those nuggets have nuclear density. So typically 1 gram of nugget has the size of a bacteria, 10⁻⁵ centimeter, really small. If you're interested in this model, want to look for the details formation process, I invite you to go to this paper here, which is a kind of a review paper of the formation process.
Sorry, these guys, the neutral star, there's no gravity.
Oh yeah, it's not gravity holding them.
Right.
It's the axion domain, which is holding them. You need the axion. So if you have the axion, then that basically holds those things together. But you are right. You can think of them as mini neutron star, except it's not gravity holding them.
And typically, how many quarks are star?
So 1 gram, you would have 10 to the 24 equivalent of mass of the proton, but that can go up to a kilo or a ton. There is no really technical upper limit. So let's go back to my sigma over m thing. Typically for those nuggets, what would be the sigma over m? This thing that relates to the interaction rate. You get a ratio that's of the order of 10⁻⁻10. Remember, for WIMPs, it's 10⁻20. And for the constraints we get from the CMB, baryonic acoustic oscillations, it's 10⁻⁷. So it is less than 10⁻⁷. It's not massively less, it's just less enough. So in this model basically behaves as CBM. And the form, yeah.
And here is sigma is interaction between your nuggets and what?
So nugget matter, nugget photon. The sigma is essentially the geometrical cross-section of your nugget. So if you have a nugget mass, nuclear density, you know what the sigma is. And in this, of course, in this process, because the formation is happening at the quark-hadron phase transition, basically has the same effect as PBH. It hides the baryons before BBN, so it doesn't mess up with BBN. Moving on to the second part. So how can we actually test this? And this is, I think, the strength of this. It's not a model that lives in some virtual reality. It's actually very testable. So I'll show you how to actually calculate things in the context of this model, and I will follow this discussion by some of the works we have in progress where we actually start testing it. And yeah. So you have two types of nuggets, matter nuggets, antimatter nuggets. Matter nuggets, they are not very interesting. They don't produce electromagnetic signature that we can detect. We can just forget about it. Antimatter nuggets are, on the other hand, very interesting because they are everywhere, and they will, of course, collide with normal matter occasionally from time to time. If you look at what happens when you have such a collision, so colliding, let's say, a proton or an atomic age, the particle, if it manages to get inside, will be annihilated. So you get 2 GeV of energy, 1 + 1, available to do something. So this 2 GeV of energy, where does it go? So that's, again, the paper I showed you, all the calculations are done and the references inside that paper as well. So from the 2 GeV energy available, some of it goes into reheating the positron sphere. So that's why I made it a bit larger here to show you it inflates somehow thermally. The positron sphere, you do the calculation, how hotter does it get? A typical annihilation like that, you can easily get temperature of EV. So you have this positron gas, which is surrounding and around the antimatter core, which gets heated at temperature of EV. Charged particles, they move around, it emits Bremsstrahlung radiation. So what kind of emission you have here is absolutely perfectly conventional Bremsstrahlung emission, which can be calculated, again, with textbook physics. At the point of entry, you also have some of the energy that gets out in form of X-rays, and you have some mesons being produced as well. The rest of my talk, I will essentially focus on the Bremsstrahlung. But you can think of applications in X-ray as well. So the formula, the flux coming out of this, reheating of the positron sphere can be calculated to get this expression. That gives you the flux. So is you have a nugget which is heated at a certain temperature T. The flux you get at frequency nu is given by this expression. All these are nugget specific things. You recognize here the exponential of the Bremsstrahlung. So essentially, it's a pure Bremsstrahlung. There is no absorption Bremsstrahlung because the optical depth is too thin for that. So you essentially have an exponential emission and a cutoff, roughly speaking, again, it's in the calculation at 1 gigahertz. But essentially, the whole thing is Bremsstrahlung, which is interesting in itself because it's absolutely not thermal emission. You do not have the Rayleigh-Jeans drop of the emission at low frequency. Pure Bremsstrahlung, no absorption. And this is precisely this plateau at low frequencies, which is the seed for what makes this model testable with observations. The temperature is not a free parameter. It's actually something you can calculate. And I'm going to show you how to calculate it. Temperature of the positron sphere. So say you have one interaction. So you have one collision of one nugget with one proton particle. That gives you 2 GeV of energy available. There is a probability F that the proton actually does not get inside, that it gets reflected. A quantum reflection that is, again, something of the order 0.10%. So 10% of your incoming protons will manage to get inside. So that reduces the available energy by a factor F. Out of which a fraction 1 of G gets into the reheating of the positron sphere, and the fraction G gets into the X-ray emission at the hotspot. So energy available per collision with the proton is 2 GeV times F times 1 minus G. Now you take this nugget and put it in a baryonic environment. So you have many interactions per unit of time. Per unit of time dt, the energy injected inside the nugget is, so the power here is 2 GeV times F minus times F times 1 minus G times the cross section of the nugget, so pi times the nugget size radius square, times the number density of baryons you have around, times delta V, which is the relative velocity between the nugget and the surrounding baryons. That gives you the power injected in the nugget. This is where you get the nugget temperature from. So again, it's not a free parameter. You know how much energy gets injected, that gives you the temperature. How you do that, you equate the power to the total flux getting out of the nugget with the nugget at a given temperature. This formula here integrated over frequency. That gives you the temperature. So if you fix your baryonic environment, you know your nugget mass, that gives you the temperature. You calculate. From that, you calculate the emissivity as a function of frequency for a given nugget temperature radiated away from the collection of dark matter particles you have within a certain baryonic environment. So essentially take the area of the nugget times the flux of given frequency and given temperature times the number density of nuggets you have in your system. That's the formula you need to calculate the emissivity of this model in absolutely any astrophysical environment, whether it's cosmological, galactic, H2 regions, whatever, that's the one you need. So let me mention one thing here, that if you do reverse engineer all the calculations and try to rewrite the emissivity as a function of number density of AQN and number density of baryons, it scales like n AQN times n baryon to some funny power. The power itself is not the point. The point is it's very different from n AQN square. And if you think of conventional dark matter models like WIMPs or dark matter interaction would actually scale like n dark matter square because it's a dark matter interaction. The reason I'm mentioning it, if you go back to the 90s, where the excess of the 511 keV line in the galaxy was detected, it triggered for a very short time excitement because people thought this could be the dark matter signature in the bulge of the galaxy. Very quickly, the idea was dismissed because that emission was actually correlated with baryons, which in the context of WIMPs and conventional dark matter is not possible. In our case, this is exactly what we expect. We totally expect that dark matter emission, electromagnetic signal will correlate with the baryons because it's entirely supported by this interaction between antimatter nuggets and surrounding baryons. So the practical implementation of the model is absolutely straightforward. You start from, you choose your astrophysical system, like I said, some cosmological system, a galaxy, whatever, which gives you a number density of baryons, number density of protons, for instance. You need to know, to do your calculation, you need to know the delta V, so the relative speed, the average relative speed between dark matter and baryons. Not something is typically you get from simulations, from hydrosims. And I'll show you the next slide, what I've done in the context of large-scale structure. From this N baryon and delta V, you get the AQN temperature. If you combine this AQN temperature with number density of AQN, which you get from the dark matter distribution, assuming a certain mass for the AQN, which is technically the only free parameter in the model. We don't know what the AQN mass is. It's more likely a mass function, but all the calculations I'm doing are assuming a single mass because it's simpler to do that. You combine those three things, it gives you an emissivity as a function of frequency for given AQN temperature, as a function of position and time if your system is anisotropic and time dependent. So let's move on to some applications here. I first looked at the first thing I will show. This is what follows is essentially work in progress. It will give you some ideas how you can implement this model in practical situations. So for this one, the first one, I was interested in the large-scale structure signature. So I worked with the magneticom simulation from a colleague in Germany, Klaus Dorlag. He has done hydro simulations that look like this. So you have, he gave me the cube at redshift 0 of dark matter and gas, which is all I need to do this calculation. So from the cube, this is all redshift 0. From the cube, if you take a slice, so I'll show you this slice in the dark matter distribution. From that cube, I get the N AQN everywhere in the cube. From the gas distribution, I get my N baryon from everywhere in the cube. So I have N AQN, I have N bar, and I have delta V from the simulation as well. It's all hydrosim. So at every voxel in the cube, I know what the three-dimensional velocity is. So I can just calculate delta V. Then I put myself in the side of the cube and ask myself, what am I going to see? This AQN interacting with the baryons. So from that cube, I actually project the cube as a sky, as visible from me from the side of the cube. And what I get is a square sky, which looks like this. So that shows you the expected signal, right? Exactly followed the recipe I showed you before. From N baryon, delta V, and N AQN, I can calculate everything. So the redshift 0 cube looked like a plane to me, and I'm showing you here the expected signal at 10 gigahertz. You pick 10 or 1, again, the signal is pretty flat in the radio band, so it doesn't really matter. But the units, it's Jansky per steradian. If you're not familiar with radio astronomy units, so the value, first of all, is very small. So 10 minus 2, 10 minus 1, the maximum. Jansky per steradian. If you are not familiar with this kind of units, you just need to know this is approximately 10 minus 5 the thermal SZ signal amplitude. So it is small, yes, but it's not ridiculously small. And in fact, it's something that SO is planning to detect. It's comparable to the Ricciam effect in terms of amplitude. And also future radio surveys cross-correlated with where dark matter is located, potentially also could give us some information. Plus, I want to add that it's just a redshift 0 box. I haven't worked with the full line of sight up to redshift 3 yet. It will only increase the signal. So it is small, but it's detectable in foreseeable future. on an intensity frequency plot where you have all the CMB related emissions, the galactic emissions, so the filtering and the synchrotron here, the AQN signal stands here. So again, it is small, but it's not impossible to detect if you think about it in the long term. Yes.
What's the cutoff at 10 gigahertz? Because SO doesn't actually go down to 10.
Yeah. Oh, you mean this bar here?
That you're sort of saying that it's a radio-ish or a centimeter signal.
Yes. It actually continues. I just didn't plot it.
Okay, that's
Yeah.
answered my question. How far is it?
No, if it goes as far as basically it can go in that context. At some point, you will hit the Bremsstrahlung exponential cutoff, and that depends on your temperature. I haven't done this calculation here because it's very small. It's buried into many things. So for that specific experiment, it's mostly the low frequency radio that's interesting. Okay, so let's move on. More hypothetical here. Let's move on to the dark ages. Okay, so way before we start forming galaxies and stars. So dark ages is that period of time which starts after recombination and ends before the formation of the first stars. Why is it interesting here? Because in this range of in this era, essentially, if you think of number density of species, they scale at 1 + z³. So everything I talked about, interaction between AQN and baryon, will be amplified by a factor of nearly 1 + z⁶. I mean, not exactly because it's not n², but approximately, right? It will be massively amplified by the fact that the density is increased a lot. So in conventional dark matter model, you don't expect to see any signature from the dark ages. In this model, you do. Because in this model, even though you don't have stars and galaxies, you do have dark matter, you do have baryons, and they interact. So what do you expect to see? So interesting thing here is if you push this sky brightness to very low frequency. So now we are looking at below the gigahertz. There is this excess here, which has been known and measured over the years, called the arcade excess, but really technically it has been known since the 80s. So what this plot shows is the intensity expressed in brightness temperature as a function of frequency. So everywhere it's flat, you're basically measuring CMB. So you are in the Rayleigh-Jeans regime of the spectrum here, where intensity drops as 1/μ². Expressed in terms of brightness temperature, it's constant. Okay, so this part is constant. This is actually the Firas data point, constant, constant, constant. And then at 1 gigahertz, something happens, starts to go up. So it goes up nearly as a square of frequency, or inverse square of frequency. So intensity becomes constant. Interesting, because in the AQN model, that's exactly what you expect to find. You expect intensity to be relatively flat at very low frequencies. There is a cutoff at megahertz, 1 or 10 megahertz, which eventually this will drop because of the interstellar medium, but don't need to discuss that. So those data points are real measurements with real experimental error bars. I tried to calculate the AQN signature, thinking, okay, assuming there is this interaction between redshift of a few dozen to redshift 1,000, what do I get? Now I have these AQNs interacting with baryons over this era. What do I get? And that's what I get. So it's kind of disturbing because there is no fine tuning here. There is one. It's the amplitude. I don't know where the amplitude falls. So I adjusted the amplitude so that it matches with the data points. Fixing the amplitude is the same as fixing a mass for the AQN. But the slope, I have absolutely no freedom here. Not at all. Because the slope is entirely driven by the emissivity of a single nugget in the flat part of the spectrum of the Bremsstrahlung emission. So again, it's not a proof of anything. It's just disturbing that it seems to agree well with this excess that so far has no explanation. This, what I'm showing you next, is also work in progress. So it has to do with CMB spectral distortion, but which is even more distant in the future. But basically, the idea is CMB is not a perfect black body. It has been measured to be very close to black body with a precision of a few 10⁻⁵. Okay? And this measurement has been done in the 90s. It has never been done again since that time. So question is, and within that range, yes, it's a perfect black body. But what if you can reach precision of 10⁻⁸, 10⁻⁹? Well, it's no longer a black body. That's the thing. So you expect to see distortion of the black body if you are able to reach very, a typical error that's 1,000 to 10,000 times smaller than that. So what's the physics here? The physics has been developed very early on in the 70s by Ludovic and many others. It was somehow forgotten until it was revived in the 90s by Joe Silk and Wayne Hu and a couple of others, and even more recently by Jens Sluba. Actually, Jens Sluba is very active in this region. And it's very interesting what's going on here. So where are these distortions coming from? If you think of so the time, starting from the Big Bang here, and let's mark two specific epochs, 2 months after the Big Bang, which is a redshift of 2 million, and a recombination time, redshift 1100. So what's happening here is that if you have any energy injection in the what will be later the CMB plasma before those 2 months, you can show that this is very quickly fully thermalized. So if you have a dark matter model, which for some reason decays into high energy particles, or you have interaction between dark matter and baryons, anything that injects energy in your system, you will never be able to see it because this injected energy will be fully thermalized anyway. The only thing it does, it changes the temperature of the plasma, but it changes it in a way that it still looks like a perfect black body. So what happens before 2 months after the Big Bang is forever hidden from us. But what happens between 2 months and recombination time, that's no longer true. In fact, you can show the thermalization is never complete. Even for conventional processes, so I'm listing just a few here, dissipation of acoustic waves, adiabatic cooling of baryons. Again, there is a long list of literature here that address this problem. The thermalization is effectively never complete. And you can show that if you reach levels, precisions of 10⁻⁸, you can actually observe these things. But why it's interesting for us who are thinking using that as a prop of dark matter, nature of dark matter, is that also energy injection from dark matter processes will also alter the CMB spectrum. So there are also papers written in this with this in mind. And I have work in progress with a PhD student. We are looking at the kind of CMB distortion we expect to see in the context of this model. That's precisely exactly where we should look. And after that, we enter the dark ages, different regime. And I mean, another well-known CMB distortion at much lower redshift is TSZ, for instance. But really here, I'm talking about what's happening before recombination. Yes.
I'm puzzled by, you said before 2 months, you said that we are not able to see any.
No.
What about olive neutrinos?
If you have energy injection that contributes to the interact with the plasma, it's gone. This information is gone. What it does is changes the temperature of the plasma in a way that it always looks like superfluid black body. If you have those neutrinos after 2 months, maybe there is a trace.
The neutrinos I'm talking really the few seconds because the one which remains after interaction between electrons and so on.
Yeah, so they don't thermally exchange with anything after those time when they are released. They are completely decoupled from the rest of the universe.
Yes, but so we can detect.
Oh, you can detect them. I'm talking about processes that couple to the plasma.
Okay.
I'm specifically talking about that. If you have an energy injection process that couples to the plasma, anything happens before 2 months, it's gone. So there was two experiments. One is Pixie, I forgot the name of the other one, which planned to precisely access this very high CMB distortion precision. It was not funded. It's a shame because I really thought it was a fantastic experiment, but effectively the detection floor of Pixie and the other one, I forgot the name, was around 1 Jansky per stereo, which again is not very far from the detection level I mentioned before. So once again, all I'm saying is we have a dark matter model here, which potentially can really be tested on actual data, on data that will come up hopefully one day. So let's move on to the galactic environment. So this is again, work in progress, nothing final here, but there are interesting thoughts about how this model can also be tested inside the galaxy. I want to compare two things, radio, the galaxy seen in radio and the galaxy seen in UV. So in radio, we have, so first discovered by WMAP, but Planck confirmed it, the so-called WMAP haze. So it's a leftover of the full sky emissivity that you can't remove after you remove the CMB, synchrotron, free, and all the things, all the sources we know about. You have this leftover for different bands, 20 gigahertz to 90 gigahertz for WMAP. It's there. It doesn't go away. And that still troubles people these days, understanding where that could come from. So that's one thing. That's the CMB seen in radio. In the UV, there was this paper that appeared in 2015, where the authors, they used the GALEX data and they reconstructed a full sky mosaic of the UV sky, FUV and near UV. And sure, you have UV signal in the galactic plane, and we actually know pretty much all the sources of UV in the galaxy because they come from stars that we know individually. But the weird thing they found is that at high, very high and very low galactic latitude, you have an excess of UV, which they can't explain. Even so, they try to build a model of the UV radiation in the background at high and low galactic latitude. Taking into account radiative transfer, they could not match the data. So they finished the paper saying, maybe this is a signature of dark matter. They used WIMPs as a potential candidate, and again, it didn't work. So why is it interesting for us? This plot illustrates what I have in mind here. If you think of the WMAP bands here in the 20-ish gigahertz region, and the UV, so the NUV and FUV are here. The AQN signal is, again, unobscured Bremsstrahlung, so pure exponential. It's very easy, but this is actually already done. It's very easy to match the WMAP haze amplitude to the AQN model, right? Because it's just a matter of finding the right amplitude, and basically you are done. Once you've done that, essentially that corresponds to a given average temperature for the nuggets, but yet you get from observations. And once you've done that, everything that happens at a higher frequency cannot be changed. It's completely fixed. So the work we have in progress right now starts from fixing the radio emission from WMAP haze and make actually a prediction in the UV. If the temperature turns out to be low for the nuggets, we would not see anything. If it turns out to be high enough, we would see something. So matching the WMAP haze is easy. It's already done. But if we get a simultaneous match with the UV background, that would be quite amazing. Yes.
But this depends on the mass of the nugget. I mean, what if you have a distribution?
It does. So it depends on the mass of the nugget. Like I said, it's probably not a single mass, but a mass function. So it introduces another degree of freedom in your modeling. But whatever you do with the mass function of the nuggets, the ratio, that ratio between intensity at different wavelengths is completely fixed because the flux curve is completely fixed once you know the temperature. So I will essentially stop here. So it's just a short story. There are many other papers we published on that. And I will finish on that. Especially the message number 0, zeroth order message is the AQN. It's not just another dark matter model. It's a realistic one where dark matter is not dark. It's strongly interacting and it's made of baryons. So it's quite all the opposite of the dark matter paradigm. And you know, it's physically sensible. It's not a completely crazy thing. And so far, it does not violate any observational constraints. The reason is that you have those big objects, I mean, gram, kilogram, their number density is extremely low. So even though they interact very strongly, the signal we can detect is very weak anyways. So what next? Well, a criticism we often get, and I totally accept it, is that so far we haven't made a single prediction. So far we effectively turn the wheel and make postdictions and confirm that the model does not violate any observational constraint. Next step, obviously, is to make a real prediction. So this is the effort we are into right now. Whether it goes from large-scale structure to the galaxy to the CMB, we are working hard to actually make a testable prediction for upcoming experiments. And I've been talking to a few people. There are things particularly interesting in the, you know, what happens in H2 regions. In the galaxy, we have those H2 regions, which are ionized. And I did not mention that, but the nuggets, as you hit them, so the positron sphere gets inflated a bit, the least bound positrons will escape the system, right? It's just a simple kinetic potential energy argument. So your nugget effectively, on average, will become electrically charged. So you end up with a dark matter that's electrically charged, which has very interesting consequences. In the H2 regions, you end up with nuggets for the antimatter ones that are negatively charged. So their cross-section will, of course, increase a lot because now you get it's not just the geometrical size, you have the Coulomb cross-section to consider. In H2 regions, the protons will just, you know, run into it. So can this effect be detected? Open question. So that's a project we have on the table as well. Beyond that, if the dark matter is electrically charged, potentially you have the seed for magnetic field, especially in the early universe. Quick back of the envelope calculation I did, the magnetic field you get from the level of electrical charge you expect is very small, nanogauss in today's universe. But that requires more attention, I think, especially in the early universe. And the charge in itself is not a problem because the mass remains very high. You get, for a nugget of 1 gram, the mass equivalent of baryon is 10 to the 24 baryonic mass, proton mass. Typical charge you get in the galactic environment is 10 to the 5, 10 to the 6. So the Larmor radius is really, really, really big, which means even though they are charged, you cannot bend charged nuggets along magnetic field. However, you have charged dark matter that flows, it will generate magnetic field in itself like an electrical current does. So those are things that potentially could lead to detections or, you know, new phenomena we can predict. Always working with that in mind, we should try to predict something that can be observed because so far it works for all observational constraints we have. So I'll stop here. Thanks.
Thanks a lot. Questions? Yes. Yes. So what about constraints from the QCD axiom per se? Because this is very constrained, right? Because so this really needs to be the QCD axiom, the same guy who solved it.
Oh yes, it cannot be the ULA for sure. So you need the QCD axiom, and the QCD axiom right now, the mass, as you know, is very constrained.
Right.
And the mass range that's still open is 10 minus 6 EV to 10 minus 3. So anywhere in this range would be okay.
So this is still open because I thought it was almost.
Oh, no, it's not. Yeah, it's still open. I mean, it cannot be lighter than that because then you have too much dark matter. Cannot be more massive than that because it conflicts with stellar evolution.
That's right. Yeah.
So that's what's left, and people are actively building detectors to find this. And once you know the axion mass, that puts constraint on the mass of those nuggets as well. So that's something interesting in itself. And the lighter the axion is, so close to 10 minus 6, essentially you'd form almost no nuggets. So all dark matter would be pure QCD axion in that case. So again, there is a range depending where the axion mass lands, 10 minus 6, 10 minus 3. You do have a lot of mostly dark matter as nuggets or not at all.
And you can also have axion dark matter in the same model. Can you have a mixture?
Yes, you can have a mixture. So anywhere in between, you have a mixture.
CMB always satisfy black body radiation type or no? CMB.
What do you mean?
CMB radiation. It is always satisfy the black body radiation diagram or not?
But he's saying no.
Staying
He's saying that there are small variations.
There are variations, so people expect variations. If you go back here, yes, it's perfect black body within 5×10⁻⁵. Yes, but people, even if you forget about dark matter energy injection, people expect to find deviations, just because so essentially you have three processes that lead to CMB thermalization: Compton, double Compton, Bremsstrahlung. Right? So you have energy mixing process. You also have photon production processes, Bremsstrahlung and double Compton. People have, again, people have done this calculation in the 70s, started with Zeldovich and Senyaev. We know that the CMB is not a perfect black body. It cannot be a perfect black body. There is simply not enough time between 2 months and 400,000 years to thermalize the plasma completely. So we do expect distortions at the level of 10⁻⁸.
Nice question. Your model of dark matter doesn't contradict at all all the simulation of the last structure formation.
No. No, because the sigma over m is too small for that. In fact, probably the large scale structure constraint on sigma over m is the weakest of all of them. It's often presented, where is it? It's often presented as a strong constraint, but it's not. 0.025 centimeter square per gram, but the AQN model, you are already in the range of 10⁻⁻10, plus or minus, depending on the mass and mass function. But it's totally behaves as CDM. So no, you don't have any signature in LSS.
Another question. Your nuggets, they are really stable?
Yes, they are stable. They are indestructible. BBN cannot destroy them. The binding energy between the quarks is of the order of the phase transition, 170 MeV. BBN, you have photons that could be maybe 10 MeV in the tail. They can't destroy them.
You mentioned that there is nuggets, anti-nuggets.
Matter nuggets and antimatter nuggets, yes.
What about the collider?
So if they collide, you get complete destruction with a signature that would be extremely strong, but the probability for this to happen is.
I remember in the past, the dark matter was supposed to collide.
Yeah. I've done the calculation. You have to wait much longer than the age of the universe for this to happen. It's just the number density is too low for this to happen in the universe lifetime so far.
So these things are neutral, right?
Yes, unless you hit them. If you hit them, the positron sphere inflates a bit, and you lose the least bound positrons. So they are not neutral. But the charge over mass ratio remains very small.
So stop then
No, because you run out of matter. There's just nothing left, because the dominant process in the transition is the matter-antimatter annihilation. So it's just gone. You have this massive production of photons, 10 billion for one. You have nothing else to form.
You mentioned X-ray radiation.
Yes. It's on my work list. I suspect it will be also very small. I don't think we will see anything really strong in clusters of galaxies. But yeah, it's something I definitely want to.
When you discuss the pixie that the experiment has said is required distortion, you meet another one.
Yes, that's the one.
So what about matter antimatter? I mean, are these guys supposed to be the same amount of anti-nuggets?
So that's the interesting thing. So it turns out this model gives us for free a solution to the matter-antimatter asymmetry, in the sense that matter, so us, antimatter nuggets and matter nuggets, they all come from the same, origin, so a mix of matter and antimatter. The asymmetry between matter nuggets, antimatter nuggets, and the leftover, which has not collapsed in nuggets, is of the order 1. So if you wanted, if we could calculate, if we could solve QC completely, this calculation that nobody knows how to solve QC completely. So all we can say is that the difference between the matter nuggets, antimatter nuggets, and leftover matter is of the order 1, and the number that works, which is of the 1, is 3 units of antimatter nuggets, 2 units of matter nugget, and 1 unit of matter that hasn't collapsed in nuggets, which is us. And you get this ratio 5:1 naturally without fine-tuning anything.
So you mean that if you add all matter in the nuggets and add, then you get
Yeah, you don't need any extra process to explain.
So why do you produce more anti-nuggets?
Because the coupling of axion to matter antimatter is asymmetric. So it comes from that. So the process of growing your nuggets, even if it starts roughly statistically the same everywhere, in the end, you don't have the same. And the difference is of order 1.
Because the coupling is chiral.
Yes. Yes.
So the CP violation in the axiom is the origin of the metals.
Yeah. But through that process of forming nuggets.
We have a question from Zoom by Gabriel Chapa. So it says, common knowledge is that the QGT transition is a crossover. The production of nuggets looks first order. Is there any
No, it
constraint
is. It is not first order. It is second order. Yeah, and I invite you to look at the paper, the review paper from. It's somewhere on my slides. Let me find it. Yes, this one. Everything is explained here. So it is actually second order, absolutely. So you don't have any density change.
Other questions from Zoom or the room? Okay, if not, let's thank the speaker again.
Thank you.